as with, I think, many of the excellent sort of specialists that we've got in the room today, we have a role that involves enabling people to, I guess, provide data, provide insight and knowledge to help professionals make better decisions about buildings and infrastructure and geotechnical assets. And I just really want to spend a little bit of time partly reflecting and partly looking forward about ways in which I think by combining multiple sorts of data, multiple types of particularly monitoring data, we can make those insights and that knowledge more useful, more reliable. I'm not actually going to start by talking about buildings or structures or railway earthworks, but actually about something which I think is probably, we'd all agree, is something a lot more important, and that is the human body. I suppose when thinking about preparing for this presentation, I was just thinking about how medical professionals operate, how they gather data, how they work, how they help to diagnose problems in a structure, in their case, in a body. And you know, you don't have to be an expert to think that if there is a suspicion of say a cancerous tumor, then an X-ray, a chest X-ray would be undertaken. I think that's no surprise. We'd all expect that. But I looked a little bit more, and I was actually pretty staggered by all the other things that they would consider. The range of early assessment approaches they might take, the portfolio of imaging techniques that they've got to hand, the ability they've got to take samples and to conduct tests on those samples, and the ability to do laboratory tests, effectively in situ tests and laboratory tests. So there's a massive range of data that they may be looking at in order to diagnose a patient, to understand the nature or the extent of a problem, and to facilitate a remediation or a repair, a healing in their case. Now, fortunately, I've never had reason to get that close to that area of science, but I have spent what seems to be quite a long kind of career, a lifetime really, working in fields, gathering data about the condition of structures. For a long time, I was responsible for a structural investigation team. I was director of a company involved in non-destructive testing. We would get asked frequently to look at a structure like a concrete floor in this case. We might do a ground penetrating radar survey of it. But we'd also do a bunch of other things. We would ask what was the nature of the problem. We'd try and understand what anecdotal evidence there is available. We would use a range of imaging techniques. We would take samples, material properties, and look at those samples both in situ and in a laboratory. And I think we would always try to take a balanced view towards arriving at something which is affordable, practical, and that would result in a report that would help the professional make a decision. So I've moved on from that area. 5 years ago, I joined Senceive, and I moved from a world where I was involved in taking data, I guess, from the here and now, from one position in space at one position in time, about what is the state of this floor here and now, to one where I'm much more involved with longer-term monitoring, providing longer-term insight into how a structure might be behaving. And I think a lot of those principles apply. Again, there's a whole range of different parameters that we can gather, that we can choose from, and that we can putting the right balance of those together as an expert in the field is very much the sort of job of the professional monitoring specialist, I think. So I want to spend a little bit of time looking at some examples of how that comes together. And I think maybe it's helpful just to look at a little bit of infrastructure, something that's got a combination of structures and geotechnical assets, but to think about how, in our case, a wireless remote monitoring condition monitoring system can be installed here. We can install things like these rather smart little tilt nodes on grids to look at movement. We can install sensors that will harvest data from third-party sensors, the inclinometer down here, getting geotechnical data. All of these things will forward the data from the sensor to a cellular gateway. They will relay that data to a cloud-based server. They will allow you as a remote user to access that data. They can send automated alerts if thresholds are breached, and they can collect long, medium, or short-term data. So a range of different sensors can be applied in the short, the medium, or the long term, and they can collect virtually continuous data on a virtually permanent basis from that structure. So I want to, I think in the limited time we've got today, just focus on a couple of different areas. The first one is an example looking at a structural monitoring project. This is a bridge in Dortmund in Germany, and it involves using a multi-sensor monitoring approach to look at a structure that was highlighted to be of interest. Now, this is probably not the most exciting bridge in Germany. It's probably not the most exciting bridge in Dortmund, but it is quite important because it's a 6-lane bridge carrying an arterial road, effectively the inner city ring road in Dortmund, over another busy local road. It was built in 1957, and it's a key part of the inner Dortmund road network. It's also quite close to Dortmund football stadium, so I'm sure a lot of people would be upset if it was out of service. A condition survey was carried out in 2022, and there was evidence of surface cracking and distress. It's quite an old structure now. It's had a lot of use. It's exceeded its design life and is carrying excess loading. Familiar story across, bridges across the world, really. And there was concern in this case about a loss of pre-stressing in the concrete deck, possible internal corrosion of the steel, possible weakening effectively of the structure. And the engineers responsible for it particularly wanted to know the way it behaved under load, the way it was deflecting under load. And a package of monitoring was put together that was started by installing a series of tilt nodes on the deck soffit in 2 lines. And so lots of these things were effectively stuck to the underneath of the bridge. And if we move on, we can see that happening. So these sensors just, in this case, just drilled into the deck soffit, into the concrete. Quite significantly, this is pretty simple stuff. It doesn't require the work of a high degree of specialism. It can be done quickly and simply. In this case, just in a relatively short road closure with access to a hydraulic access platform. And these things. A couple of things about them. They do a range of different things. First of all, they measure rotation. They're a triaxial tilt sensor, so they're measuring rotation to within a thousandth of a degree. Very, very precise measurements. They also measure temperature, so it's possible to get an understanding of how, for example, the effects of the diurnal changes, whether the sun hitting the bridge structure is having an effect. So we can do temperature compensation on the data, and they communicate in a mesh network via a gateway so that you can see the data without having to visit site. But a number of other sensors were installed within the same wireless network so that they're all harvesting data to remote users in the same way. At mid-span on both bridges, on both sides of the deck, strain gauges were installed so that the effective loading could be assessed. And where there were cracks on the deck, a number of crack sensors were installed, which enabled us to look over time, over the course of a day or a week or a year, how those cracks were changing in terms of their extent. The other thing that, first point, those sensors were all installed at the start of a 6-month monitoring program. So they were installed, then they were left sampling at 30-minute intervals for a period of 6 months to build up a baseline data set. After that 6-month period, there was another road closure and another batch of data were collected. That included using laser scanners to look at the behavior of the bridge structure. And the reason that that was done at that stage was the exciting bit, really, was that our friends at Dortmund Council pulled some strings and got the fire brigade to lend them the biggest truck that they could find, a 48-ton crane, which could be used to provide this dynamic load on top of the bridge deck. So there's a bunch of people underneath the bridge looking at the effect of moving that truck in various positions across the width and the span of the bridge deck. So instead of collecting data at 30-minute samples, the wireless system was set to record effectively live data at 30-second periods. That data could be seen in real time on a laptop. You could see as the truck was moved, you could see the effect of it on the strain data and on the displacement data from the tilt nodes. So if we look at that in a little bit more detail, we can see this this data quite clearly. On the x-axis, you're looking at time. You're looking at a period of about 30 minutes from there, 11:40 through to 12:12 here. The top graph, as you can maybe able to see, is microstrain, so the effect of the loading. The bottom is showing the displacement in millimeters of the deck from the tilt nodes. It's pretty clear at which point the truck was rolled onto the deck. It's very easy to see when it went on there, the effect of it, and when it rolled off. The reason for these, particularly the shape of this graph, is that these two lines, the two orangey yellow ones, are one side of the load, and the two blue ones are the opposite side of the truck. So one set are leaning in towards the load, and the other ones are further down the road, down the bridge, and they're leaning the opposite direction towards it. They're both moving to the same degree of magnitude. The loading effect is the same, but one's leaning this way, and the others are leaning this way. So at the same time as the wireless system was collecting data, the laser scanning system was collecting millions of points, building up a surface terrain model of the bridge soffit. And from that, and you certainly don't get any prizes in picking out where the truck is located in this plot, the darker blue indicating the greater deflections. Putting those two data sets together in this graph, you can see that the tilt data is displayed in green, and the laser data is on the blue line here. So again, there's a high degree of correlation. For the cynics in the room who would say that you have to do a laser scan survey to get the level of precision, well, actually, the precision is virtually the same, within 1/4 of a millimeter for both of those two data sets. So there's a high degree of corroboration between those two sets of data independently collected. This one was from the outside of the bridge deck. We've got a maximum deflection there of about 2 millimeters under the load. Now, outside the bridge, you've got less mass, the bridge is less stiff, you're further from the supports. So we also repeated the exercise, moving the truck in a lane. And interestingly, we got maximum deflection of just 1.4 millimeters there. So it's about 50% less deflection because the bridge is effectively stiffer towards the central supports. So I think what that project showed us was that you can bring together a bunch of different sensors that collect mechanical data, for example, strain, with effectively movement data in the form of displacement. They can tell a consistent story. They can explain the distribution of movement and the way that pattern of loading affects the structure. And you can see how that changes over time. The laser scan, of course, gets a complete picture, a very precise picture across the entire structure, but only at that time, that place and time. It needed a road closure, it needed line of sight. It's something that you do occasionally, maybe every few years. The tilt sensors could remain in situ for 10 years before they need a battery change. So they provide near continuous data on a near permanent basis. And I think it's that sort of combination that is quite powerful. The next example that I have is around a different area altogether. A lot of what our users employ these kind of approaches for is looking at slope stability and the risk of landslides, particularly affecting railways. Last year, I presented somewhere over there on how Network Rail have conducted a sort of industrial scale rollout of wireless monitoring. They've employed more than 50,000 tilt sensors, 1,000 cameras. They've taken something like 6 million photographic images triggered by movement of the ground. So they've used this system on a big scale to look at the risk of landslides and to get early warning of landslide risk. And I want to just look at a couple of multi-sensor options here, which look at much more specialist areas. The first of them is drainage, and the second one relates to the detection of rockfall events. So they're still involved with slopes, but they're a little bit more specialist. So the first one is around drainage and flood monitoring. Now, the effects of water on slopes is very significant. Wet ground, you're looking at reduced friction, you're looking at increased loading on a slope. So therefore, you're looking at an increased risk of unfortunate events like these, which cause damage, danger, disruption to the railway network. And these type of events are quite common, even when they don't result in an actual slope failure. Even floodwater on the surface like this can cause interference and disruption to signaling and communications and to electrification. So they can stop the railway performing effectively and safely. Unfortunately, these problems are becoming more common. They're on the increase. The number of high consequence earthwork failures in the last decade has virtually doubled. And the reason for that is that our winters are warmer and they are wetter. So that's a picture from last February 24, and we were looking at the result of a very wet period of weather. The bit of the country that I'm from in here had 3 times as much rainfall as normal in last winter and also in the previous year. So we may have just had a dry spring, but the last 2 years extremely wet, and they resulted in a very high number of failures. So we were tasked with coming up with some sort of cunning plan to help to reduce to that risk, to mitigate that risk. And we took a number of different sensors and ways of mounting and operating them and put them together into a package that looks a little bit like this. If you take the example of a railway structure here, up here in the top left corner, we can bring a weather station to site and we can hook that into our wireless network so that, again, you have automated alerts, you have continuous monitoring without having to visit site of that weather station. We've got very localized data on precipitation. You can include soil moisture monitoring within that package so that you've got a good understanding of what's happening in the near surface in terms of moisture. Tilt sensors can tell you whether that near surface ground layer is moving. And water level sensors, which typically take the form of a laser displacement sensor mounted at the top of a tube with a float in the bottom, looking at the distance between the float and the sensor. So the water level rises and the float will move up and down. That can be done in many different environments, in open channels. It can be done in pipes and drains and in culverts. And then a camera which can provide imagery of the site any time of day and night, most types of weather condition, an autonomously solar powered camera that can collect high quality images that can be triggered by other parts of that system, by movement, for example. So that comes with all of the advantages of a responsive wireless system. All those things like automated alerts, multiple levels of alert, dynamic sampling, waking up from a sort of low power mode to a rapid sampling mode to provide quite a complete picture of what's happening in terms of the effect of high rainfall on a vulnerable asset like a piece of railway. So just to give an indication, I think, of the value of these cameras as part of the system. This is a site in southwest England, and this picture, you may not see down here, that's taken just before 5 o'clock on a Monday afternoon. You can see there's a build-up of water. This picture is taken at 3 a.m. on the Tuesday morning, the next day. The light compensation, that's not done with a flash, that's just done with the software in the system to take that picture on a long exposure and with light compensation. The water has pretty much soaked away, but significantly, there's the scar here where a whole load of that slope has given way. And a lot of sandy, loose material has fallen down the side here and come down next to the track. Fortunately, in this case, mostly connected by this temporary wall here. So that happens automatically. That picture was taken because the tilt nodes had detected movement. So it's a smart system that 3 o'clock in the morning, you do not need an engineer out on site. You're getting an alert to your team, even potentially signaled through to the to the signal box, to the control about that situation. Again, use of the camera. In this case, you've got the water level meter. This is a site near a substation that was prone to flooding. So within this catch pit, we've got a water level meter. And you can see the effect of a sudden downpour of rain. If there was a pipe blockage in there, a gradual build-up, you'd see that within that remote system. And the cellular system can work there, even with the cap over the catch pit. And a camera can be incorporated as well. So it's a sort of joined-up system that allows responsive monitoring with multiple levels of alert. And so as that sensor picks up water level movement at different levels, you can set it it's your choice. If you decide what is a significant level of increase in water level, and you can get a green alert will just go through to your database and doesn't wake anybody up. A red alert sends bells and whistles going everywhere, and the whole team are told to get out of bed and get to site. So that's drainage. Finally, I just wanted to highlight another area where I think it's beneficial to bring together multiple sensors. And I've basically got a video to finish off with here around this area of rockfall monitoring. This is maybe not such a huge problem in the UK as it is in some of the other parts of the world. Particularly, our clients in Europe and in the Alps are very interested in this. So this involves a number of different sensor types. We can have draw wires with gauges monitoring the tension on those wires. This will pick up detection of a gradual accumulation of debris on a catch fence, on a fence. We can fit tilt nodes to those stakes to pick up rotation if the whole fence is moving. And even when there is a glancing blow, an accelerometer within those tilt nodes will pick that up. If there's a sudden spike, it will wake up from its low power mode and collect that response. In any situation, it can trigger the camera to get a picture, to send that data, to send you a picture of the site. So you can understand, okay, an event has happened. Has the catch fence caught it and kept it away from my road or my railway or my pipeline, my other vulnerable asset? Or has it left a rock sitting in front of the morning express train? So I think it's that sort of combination, multiple sensors combined with cameras that can provide that powerful package. So that pretty much brings me to where I was aiming to be. Gone over a little bit there. I just really go back to the beginning here, really, because I think that if you consider the parallel with the medical world, you wouldn't expect your doctor, your medical profession, to make an important diagnosis on the basis of your blood test or your blood pressure. You'd expect a package of investigation, and I think the same should apply when we're considering critical assets like bridges, dams, and railways.